When we think of special relativity, we think of its originator, Albert Einstein. Here's our Mary Jew artwork again. Special relativity is a fundamental theory concerning space and time. Special relativity is special in that it deals with uniformly moving reference frames, ones that aren't accelerating. General relativity, which we'll discuss later, is general and deals also with accelerating systems. The general theory of relativity presents a new theory of gravity, one that, interestingly, corresponds to Newton's theory of gravity for less than enormous masses. For black holes, it's a different story. Then general relativity diverges from Newton's theory. As said, more about general relativity later. The story of Einstein's early years and how he came to his revolutionary ideas is left to your reading, all fascinating. There you'll learn why Einstein postulated that the speed of light in free space is the same for all observers, regardless of any motion relative to the light source. If a light source moves toward you or moves away from you, you know what? You will always measure the same speed for light. Even if you're in a spaceship moving away from a light source at half the speed of light, you'll measure the speed of light from that source to be the same as if no motion were occurring. Why that is true involves the special relationship between space and time. After all, speed is a ratio of space and time. It just so happens that you can't change one without changing the other. The distance that light travels per amount of time taken is a constant, the same for all observers in all circumstances. So we find space and time melded together to make up what we call space-time. Quite remarkable. Einstein went further. He postulated that nature's laws are the same in all uniformly moving systems. If you perform an experiment in your basement, done correctly, the results would be the same if you performed the same experiment traveling at constant speed in a supersonic aircraft. Furthermore, no experiment can distinguish between uniform motion and rest. You've been in a bus and thought you were moving when you discovered that you're at rest and the bus next to you moves? This can be confusing. If it's done in space where there aren't any background clues, you wouldn't be able to tell who is moving. Are you moving or the other guy? A lot to think about. One major prediction of special relativity, confirmed by countless experiments, is time dilation. If you watch two identical clocks, one moving relative to you and one at rest relative to you, you'll observe the moving clock to tick more slowly. Really. Time dilation is nicely expressed in the twin paradox, where one twin stays at home and the other takes a high-speed rocket ride and returns years later. But their reunion is startling, for the stay-at-home twin is aged more than the traveling twin. True or just fiction? True indeed, as countless experiments have verified, with twin particles and twin clocks, not twin people. The explanation involves both twins not only being in different places in space, but experiencing different spans of time. Want to age slower than your kid sister? Then keep moving. The twin trip is nicely animated in my video, Relativistic Time Dilation. Another prediction is length contraction. Hold a meter stick in front of you and compare its length to another meter stick whizzing by you at high speed. The moving meter stick will be measured to be shorter than yours at rest. And perhaps the most remarkable prediction of special relativity, with enormous consequences in today's world, is the equivalence of mass and energy, written as E equals mc squared. Recall that we've discussed this in connection with the fission and fusion of atomic nuclei. Energy and mass are two sides of the same coin. The mass of an apple you hold in your hand is congealed energy. If you could convert even a tiny bit of its mass to energy, you'd have more than you bargained for. And I don't have to remind you of the tiny bit of matter in a nuclear bomb that is transformed to an awesome amount of energy. When you shake the apple to and fro, you feel its inertia. That inertia, as said, is congealed energy. So you're shaking energy when you shake the apple. Einstein's ideas present a whole new way of looking at nature. The results of these ideas are far-reaching. Even the GPS systems we use every day have to take account of the effect of motion on time and of gravity on time. So let's learn more about special relativity. But first, I want to ask you a question. Einstein speaks about time being stretched under certain conditions. What is the name given to the relativistic stretching of time? Until next time, good MC square. One of Einstein's remarkable postulates is that time can be stretched. Let's examine that idea. Imagine that we are somehow able to observe a flash of light bouncing to and fro between a pair of parallel mirrors, like a ball bouncing to and fro between a floor and the ceiling. If the distance between the mirrors is fixed, then the arrangement constitutes a light clock, because the back and forth trips of the flash take equal time intervals. Every reflection is a tick of the light clock. Suppose this light clock is inside a transparent, high-speed spaceship. If you're inside the ship and watch the light clock, you see the flash reflecting straight up and down between the two mirrors, just as it would if the spaceship were at rest. You'd see no unusual effects. We say that you and the clock share the same reference frame in space-time. Suppose now that your observer friend is standing on the ground as the spaceship whizzes by her at a high speed, say half the speed of light. She doesn't see the light path as simply up and down motion, because each flash moves horizontally while it moves vertically between the two mirrors. So she sees the flash following a diagonal path. Furthermore, notice that from her earthbound frame of reference, the flash travels a longer distance as it makes one round trip between the mirrors. That's right, a longer distance as she sees it. Here's the interesting part. Because the speed of light is the same in all reference frames, postulated by Einstein, the flash must travel for a correspondingly longer time between the mirrors in her frame than in your reference frame as you ride along with the spaceship. Ticks of the clock are slower for her. This follows from the definition of speed, distance divided by time. The longer diagonal distance must be divided by a correspondingly longer time interval to yield an unvarying value for the speed of light. This stretching out of time is called time dilation. Get this. Although we've considered a light clock in our example, the same is true for any kind of clock. All clocks run more slowly when moving than when at rest. Time dilation has to do not with the mechanics of clocks, but with the nature of time itself. Quite remarkable. Or in other words, quite yum-yum. Let's apply a bit of geometry and algebra. The light clock is shown in 3 successive positions. The diagonal lines represent the path of the light flash as it starts from the lower mirror at position 1, moves to the upper mirror at position 2, and then travels back to the lower mirror at position 3. Distances on the diagram are labeled CT, VT, and CT sub 0, which follows from the fact that the distance traveled by a uniformly moving object is equal to its speed multiplied by the time. The symbol T sub 0 represents the time it takes for the flash to move between mirrors as measured from a frame of reference fixed to the light clock. This is the time for straight up or down motion. The speed of light is c, and the path of the light is seen to move a vertical distance c t sub 0. This distance between mirrors is at right angles to the motion of the light clock and is the same in both reference frames. The symbol t represents the time it takes for the flash to move from one mirror to the other as measured from a frame of reference in which the light clock moves with speed v. Because the speed of the flash is c, and the time it takes to go from position 1 to position 2 is t, the diagonal distance is ct. During this time t, the clock, which travels horizontally at speed v, moves a horizontal distance vt from position 1 to position 2. Are you following this? As you can see, these three distances make up a right triangle in which CT is the hypotenuse, and C, T sub 0, and VT are the legs. Let's apply the well-known Pythagorean theorem of geometry that states that the square of the hypotenuse is equal to the sum of the squares of the two legs. Watch the progression. Bringing VT squared to the left side, removing parentheses, factor T square out, divide both sides by C square, and C square over C square is 1. Rewrite, and taking the square root of both sides, we get the time dilation equation. Is this not yum? A major equation of special relativity derived with simple geometry and a bit of algebra. So we have the mathematical relationship between the time t sub 0, call it the proper time, in the frame of reference moving with the clock, and the time t, measured by viewing the same clock in another reference frame, call it the relative time. Here v represents the speed of the clock relative to the outside observer, the same as the relative speed of the two observers, and c is the speed of light. Let's check to see this equation makes sense. Suppose we're in a high-speed spaceship and we wish to look at our own watch to see how long the second hand takes to make a revolution. What's the value of v in this case? Note that there's no relative motion between us and the clock being viewed. So the v in the equation is 0. So plugging in 0 for v, sure enough, we see t equals t sub 0. No difference between t and t sub 0. Incidentally, I might add, relativity effects are always attributed to the other guy. Let's check the other extreme. Suppose the watch we're observing is moving at speed c. Then substituting c for v, we get c squared over c squared equals 1, and 1 minus 1 equals 0. So the denominator of our equation is 0. T sub 0 divided by 0 is undefined, but can be interpreted to be infinity. Infinity? That means it would take an infinite time to see the second hand make one revolution. That's one of the reasons we say no material object can travel at the speed of light. Let's look at time dilation with some other numerical values. Suppose that v is 50% the speed of light. Then we substitute 0.5 c for v in the time dilation equation and, after some arithmetic, find that t equals 1.15 t sub 0. This means that if we examined a clock on the spaceship traveling at half the speed of light, we'd see the second hand take 1.15 minutes to make a revolution, whereas an observer riding with a clock would find it takes 1 minute. Let's go even faster. If the spaceship passes us at 87% the speed of light, see how t equals 2 t sub 0? We'd measure time events on the spaceship taking twice the usual intervals because the hands of the clock on the ship would turn only half as fast as those on our own clock. Events on the ship would seem to take place in slow motion. Let's boost our speed up to 99.5% the speed of light. We see then that t equals 10 t sub 0. We'd find that the second hand of the spaceship's clock had taken 10 minutes to sweep through a revolution requiring 1 minute on our clock. Time dilation is not an illusion. It is real. Moving clocks run slow. This would be a good time to view my video, Relativistic Time Dilation, which examines the twin trip, where a twin that takes a high-speed rocket trip ages differently than a stay-at-home twin. Quite interesting. In the meantime, I want to leave you with a question. First, while you're in a spaceship leaving Earth at half the speed of light, you apply the time dilation equation to two cases. First, measuring your own pulse rate. Second, measuring the pulse rate of the friend at rest back on Earth. Here's my question. How will the values of v in the time dilation equation differ for the two cases, and what does this tell you about relative pulse rates? Until next time, good energy.
Where did the time go? Does anybody know? When did the day break? Did someone drop it? Was it a mistake?
Did you know that time's different when you move at different speeds? That when you move through space, you change the rate at which you move into the future? Well, you can't really notice these differences for everyday speeds, but for really high speeds, like for rockets traveling about half the speed of light, these time differences can be noticed. Let's take a look at the so-called twin paradox.
Well, bye. I don't know. I'll see you again.
Yeah, I guess maybe we're pretty interesting. Sure, you know, well, it's all in the
dark out there.
Well, it is dark.
We brought lunch, you know.
Now, while the traveling twin experiences weeks, the stay-at-home twin experiences years.
Something. No, I think I'll just sit here and do nothing. Yeah, that sounds like, yeah, I'll do that. Oh, what? What is going on out there? Oh, my goodness! I
don't believe it.
I wish I could see you. I must relax. I can't relax. I'm too old to relax.
Look at the style.
Look at the size of this one, would you?
Could a situation like this be true? You bet it can. This is time dilation. We can see time dilation by comparing clocks from different frames of reference, say from the Earth and from a high-speed rocket ship. Now, a clock can be anything that measures periodic intervals of time. To simplify, we're going to let the ticks of our clock be periodic flashes of light. Look at the light flashes emitted by the stationary rocket ship. Now, some time goes by before they reach the distant planet, but since there's no relative motion involved, successive flashes get to the planet at regularly spaced intervals. That's to say, both the sender and the receiver will agree on the time intervals between the flashes. Now, there's nothing unusual about this. But suppose the rocket ship moves. Look at the Doppler effect. An observer sees the flashes at shorter intervals. Suppose the ship moves fast enough so an observer sees the flashes at intervals twice as short as the ship sends them. Then if the ship moves away, just as fast now, an observer is going to see intervals twice as long. Like if the rocket sends a flash every 6 minutes, they'll be seen every 12 minutes by the observer when the rocket moves away, but every 3 minutes when the rocket's approaching. Now let's apply this to time dilation. If the ship passes by the Earth and moves away at the same high speed for 1 hour, and quickly turns around and then returns in 1 hour, rocket ship time, this 2-hour trip is seen by the Earth as taking place not in 2 hours, but in 2.5 hours. And this is because the ship and the Earth have been in completely different realms of time. Let's look at this in greater detail. Suppose that when the ship goes by the Earth, that clocks on Earth and on the ship are synchronized to 12 noon. Then as the rocket leaves the Earth, a flash of light is emitted by the ship every 6 minutes. That's 6 minutes rocket time. Then the ship emits 10 of these 6-minute flashes while going away from the Earth. The 10th flash is going to be emitted 60 minutes after leaving the Earth. Then the ship's clock is going to read 1 o'clock just when this 10th flash is emitted. Now suppose this is the moment that the ship turns around. Our Earth observers don't see the turnaround until they see the 10th flash. Now here it comes. It's going to take some time for it to get to them. Closer, closer, closer. Bam, there it is. 10 flashes, 12 minutes apart. That's 120 minutes, 2 hours. So that means it's 2 o'clock now on Earth. Now the 10 flashes the ship emits when approaching the Earth, they're going to be seen 3 minutes apart, or all 10 in 30 minutes. The first is 3 minutes after 2 o'clock, Earth time. The next is 3 minutes later, and so on, until the last flash is emitted just as the ship whizzes past the Earth. And that's going to be 2:30, Earth time. So a clock aboard the rocket ship reads 2 o'clock, while a clock on the Earth reads 2:30. This checks out. Check the figures. Now let's go through this once again. Watch carefully and compare the clocks. We'll get the same result if we switch frames of reference. The Earth will send flashes now at 6-minute intervals, and the rocket ship will observe them while again departing and returning on what for the ship is a 2-hour journey, 1 hour out and 1 hour back. While going away, the ship's going to see flashes 12 minutes apart. That means it's going to see a total of 5 flashes during this hour of going away. See that? Now while returning, the ship sees flashes 3 minutes apart. It's going to see a total of 20 during the hour of return. For the round trip then, the Earth emits a total of 25 flashes. At 6-minute intervals, that's 150 minutes, or 2.5 hours. Same results as before. So from either frame of reference, a person on Earth ages more than a person in a high-speed rocket ship. It's not so much a question of who's moving and who isn't, but rather the different space-times experienced. The person on Earth remains in one space-time throughout the experiment, whereas the person in the rocket ship is in a completely different realm of time while traversing space going away from the Earth, and in still another realm of time while traversing space and coming back to the Earth. That's two space-times. Two space-times separated by the acceleration of the ship and turning around. The principal significance of that acceleration is that it marks the changing from one space-time to another. Now, our twins have been in different space-times, and they can meet again at the same place in space, but only at the expense of time. Isn't that great? That's time dilation. Peace.
Where did the time go? Does anybody know? When did the day break? Did someone drop it? Was it a mistake? I've got a notion, circular motion, I'm flying out in the ocean of time.
You know that if you jog at 1 meter per second atop a train bed that moves at 10 meters per second, your speed relative to the ground is 11 meters per second. The two speeds simply add. And you know that if you jog at the same speed of 1 meter per second in the opposite direction on the moving train, your speed relative to the ground is 9 meters per second. Here you subtract your 1 meter per second speed. But are these numbers correct? The 11 meter per second and 9 meter per second speeds? Well, guess what? Not quite. What you know is almost correct. Taking special relativity into account, these speeds are very nearly, but not exactly, 11 meters per second and 9 meters per second, respectively. For everyday objects in uniform motion, that's motion without acceleration, we ordinarily combine velocities by this simple rule: v equals v sub 1 plus v sub 2. But this rule does not apply to light, which always has the same velocity, c. Strictly speaking, this common sense rule is an approximation to the relativistic rule for adding velocities. I won't go through the long derivation, but simply state the rule. v equals the sum of the velocities divided by 1 plus the product of the velocities divided by c squared. The numerator of this formula makes common sense. But this simple sum of two velocities is altered by the second term in the denominator, which is significant only when both v sub 1 and v sub 2 are close to the speed of light, c. As an example, consider a spaceship moving away from you at velocity 1/2 c. Suppose that it fires a package in its direction of motion, also away from you, at a speed of 1/2 c relative to the spaceship. How fast does the package move relative to you? There's two speeds involved. The simple non-relativistic rule would say that you add 1/2 c to 1/2 c and get c, whereupon the package moves at the speed of light in your reference frame. Not so. Relativistically, the outcome is quite different. Plugging in these values, we see Aha! 8/10 the speed of light. This illustrates another consequence of relativity. No material object can travel as fast as or faster than light. Suppose that the spaceship instead fires a pulse of laser light in its direction of travel. How fast does the pulse move in your reference frame? Plugging in these values, we see aha! You see the pulse moving away from you at speed c. No matter what the relative velocities between two frames, light moving at c in one frame will be seen to be moving at c in any other frame. If you try chasing light, you can never catch it. Little Nellie Newton tries measuring the speed of light as it passes between her fingers. In each case, that speed is c. Relativity has truly changed and elevated our thinking. I want to leave you with a double question. What is the maximum value of v sub 1, v sub 2 over c squared in an extreme situation, and what is its smallest value? Until next time, good energy. As objects move through space-time, space as well as time changes. In a nutshell, space is contracted, making the objects look shorter when they move by us at relativistic speeds. This length contraction was first proposed by the physicist George F. Fitzgerald and mathematically expressed by another physicist, Hendrik A. Lorentz. Whereas these physicists hypothesized that matter contracts, Einstein saw that what contracts is space itself. Nevertheless, because Einstein's formula is the same as Lorentz's, we call the effect the Lorentz contraction. Where v is the relative velocity between the observed object and the observer, c is the speed of light, L is the measured length of the moving object, and L sub 0 is the measured length of the object at rest. Suppose that an object is at rest so that v equals 0. When we substitute v equals 0 in the Lorentz equation, we find L equals L sub 0 as we would expect. No change in length. When we substitute various large values of v in the Lorentz equation, we begin to see the calculated L get smaller and smaller. Lisa Lorenz holds a meter stick and sees another meter stick whiz by her at 87% the speed of light. She measures the moving stick to be contracted to half its original length. If the stick were moving at 99.5% the speed of light, she'd measure its contraction to be 1/10 its original length. If the stick were somehow able to move at c, its length would be 0. This is one of the reasons we say that the speed of light is the upper limit for the speed of any moving object. A limerick popular with science types is, "There was a young fencer named Fisk, whose thrust was exceedingly brisk. So fast was his action, the Lorentz contraction reduced his rapier to a disc." Interestingly, contraction of any object takes place only in the direction of motion. As the speed of this horizontally moving baseball increases, length in the direction of motion decreases, but lengths in the perpendicular direction do not change. No contraction takes place vertically. Here's Lisa Lorenz again, holding her meter stick as a spacecraft whizzes by. We see two parallel meter sticks. Which is contracted? From Lisa's frame of reference, she sees contraction of the spacecraft meter stick. From the point of view of an observer in the whizzing spacecraft, Lisa's meter stick is contracted. So relative to Lisa, the spacecraft stick is contracted. Relative to an observer in the spacecraft, Lisa's meter stick is contracted. So again, which is contracted? Our answer is that it's all relative. And there's a nice lesson to learn here. The effects of relativity are always attributed to the other guy. Length contraction should be of considerable interest to space voyages. The center of our Milky Way galaxy is about 25,000 light-years away. Does this mean that if we traveled in that direction at the speed of light, it would take 25,000 years to get there? From an Earth frame of reference, yes. But to the space voyages, decidedly not. At the speed of light, the 25,000 light-year distance would be contracted to no distance at all. The imagined space voyages would arrive there instantly. For hypothetical travel near the speed of light, length contraction and time dilation are just two faces of the same phenomenon. If astronauts go so fast that they find the distance to the nearest star to be just 1 light-year instead of the 4 light-years measured from Earth, they make the trip in a little more than 1 year. But observers back on Earth say that the clocks aboard the spaceship have slowed so that they tick off only 1 year in 4 years. That's of Earth time. So both agree on what happens. The astronauts are only a little bit more than a year older when they reach the star. One set of observers say it's because of length contraction. The other set say it's because of time dilation. Both are right. If space voyagers are ever able to boost themselves to relativistic speeds, they will find distant parts of the universe drawn closer by space contraction, while observers back on Earth will see the astronauts covering a greater distance because they age more slowly. Yum physics. I want to leave you with a question. First, this is my friend Bob Miner's pride and joy, a 1947 Packard, a nice long automobile. Here we see it's contracted at high speed, and to half its length when whizzing by at enormously high speed. My question is this: how fast is the car traveling when its contraction is 1/2 its normal length? Until next time, good energy. Einstein linked not only space and time, but also mass and energy. A piece of matter, even at rest and not interacting with anything else, has an energy of being. This is called its rest energy. Einstein concluded that it takes energy to make mass and that energy is released if mass disappears. The amount of energy E is related to the amount of mass M by the most celebrated equation of the 20th century. E equals mc squared. The c square is the conversion factor between energy units and mass units. It's the ratio of rest energy to mass. Please realize that c squared in this equation has nothing to do with light and nothing to do with motion. It just links the way we measure energy to the way we measure mass. The magnitude of c squared is 90 quadrillion joules per kilogram. 1 kilogram of matter has an energy of being equal to 90 quadrillion joules. Even a speck of matter with a mass of only 1 milligram has a rest energy of 90 billion joules. So we see that, because of the large magnitude of c squared, a small mass corresponds to an enormous amount of energy. Recall that nuclear fission and fusion release huge amounts of energy, all in accord with E equals mc squared. To the general public, E equals mc squared is synonymous with nuclear energy. If we were to weigh a fully fueled nuclear power plant and then weigh it again in a week later, we'd find that it weighs slightly less, about 1 gram less for every kilogram of fuel that underwent fission in that week. Part of the fuel's mass has been converted to energy. Now get this. If we were to weigh a coal-burning power plant and all the coal and oxygen it consumes in a week, and then weigh it again with all the carbon dioxide and other combustion products that came out during the week, we'd also find that it weighs slightly less. About 1 part in a billion has been converted. So again, mass has been converted to energy. Get this, if both plants produce the same amount of energy, the mass change will be the same for both, whether energy is released by nuclear or chemical mass conversion, makes no difference. The chief difference lies in the amount of energy released in each individual reaction and the amount of mass involved. Fissioning of a single uranium nucleus releases 10 million times as much energy as the combustion of carbon to produce a single carbon dioxide molecule. Hence, a few truckloads of uranium fuel will power a fission plant, while a coal-burning plant consumes many hundred car trainloads of coal. Our little mascot mouse nicely emphasizes the equivalence of mass and energy.
A power plant that delivers 90 terajoules of energy to its consumers is equivalent to saying that it delivers 1 gram of energy to its consumers.
Mass and energy are equivalent. When we strike a match, phosphorus atoms in the match head rearrange themselves and combine with oxygen in the air to form new molecules. The resulting molecules have very slightly less mass than the separate phosphorus and oxygen molecules. From a mass standpoint, the whole is slightly less than the sum of its parts, by amounts that escape our notice. For all chemical reactions that give off energy, there is a corresponding decrease in mass of about 1 part in a billion. For nuclear reactions, a decrease in mass by 1 part in 1,000 can be directly measured by a variety of devices. This decrease of mass in the Sun by the process of thermonuclear fusion bathes the solar system with radiant energy and nourishes life.
The Sun converts 5 megatons of mass per second to radiant energy. In 1 million years, only 1/10,000,000th of its mass is converted to radiant energy.
Thermonuclear fusion in the Sun has been going on for the past 5 billion years, and there is sufficient hydrogen fuel for fusion to last another 5 billion years. It's nice that the Sun has so much mass. The equation E equals mc squared is not restricted to chemical and nuclear reactions. A change in energy of any object at rest is accompanied by a change in its mass. The filament of a light bulb energized with electricity has more mass than when it is turned off. A hot cup of tea has more mass than the same cup of tea when cold. A wound-up spring clock has more mass than the same clock when unwound. But these examples involve incredibly small changes in mass, far too small to be measured. But they're there. Even the much larger changes of mass and radioactive change were not measured until Einstein predicted the mass-energy equivalence. Now, however, mass-to-energy and energy-to-mass conversions are routinely measured. Consider a coin with a mass of 1 gram. You'd expect 2 of the same coins to have a mass of 2 grams, 10 coins to have a mass of 10 grams, and 1,000 coins piled in a box to have a mass of 1 kilogram. Not so if the coins attract or repel each other. Suppose, for example, that each coin carries a negative electric charge so that each coin repels all other coins. Then forcing them together in the box takes work. This work adds to the mass of the collection. So a box that contains 1,000 negatively charged coins has more than 1 kilogram of mass. If, on the other hand, the coins all attracted one another, as nucleons in the nucleus attract one another, it takes work to separate them. Then a box of 1,000 coins would have a mass slightly less than 1 kilogram. So the mass of an object is not necessarily equal to the sum of the masses of its parts, as we know from measuring the masses of nuclei. The effect would be dramatically enormous if we could deal with bare charged particles. If we could force together a number of electrons whose masses add separately to 1 gram into a 10-centimeter diameter sphere, the collection would have a mass of more than 40 billion kilograms. The equivalence of mass and energy is indeed profound. The equation E equals mc squared is more than a formula for the conversion of mass into other kinds of energy, or vice versa. It states even more, that energy and mass are the same thing. Mass is congealed energy. If you want to know how much energy is in a system, measure its mass. For an object at rest, its energy is its mass, called its rest mass energy. And with motion, its energy is even greater. Energy, like mass, exhibits inertia. Shake a massive object back and forth, it is energy itself that is hard to shake. In radioactivity and even in fission and fusion, only a small part of the nuclear mass is transformed to energy. But with antimatter, 100% of mass can be transformed to energy. Antimatter was predicted by the British physicist Paul Dirac in 1928 and discovered in the lab by American physicist Carl Anderson in 1932. Anderson discovered the positron, the antiparticle of the electron, by the track it left in the cloud chamber. The positron is equal in mass and spin to the electron, but opposite in charge. When a high-frequency photon comes close to an atomic nucleus, it can create an electron and positron together as a pair, thus transforming energy into mass. The created particles fly apart. The positron is not part of normal matter because it lives such a short time. As soon as it encounters an electron, the pair is annihilated, sending out 2 gamma rays in the process. Then mass is converted back to radiant energy. This is amazing stuff. So we see that the equation E equals mc squared tells us that energy and mass are 2 sides of the same coin. I want to leave you with a question. First, it's nice to look at things from more than one point of view. Scientists are expert at that. So here's my question. Can we say that E equals mc squared tells us that when and if matter travels at the speed of light squared, it transforms to energy? Until next time, good energy. How do the findings of quantum mechanics correspond to Newtonian physics? And now we ask how special relativity corresponds to Newtonian mechanics. Niels Bohr came up with a useful way of answering these questions. He stated that any new theory or any new description of nature must agree with the old where the old gives correct results. This is called the correspondence principle. Bohr was thinking of quantum theory, but the same idea applies to relativity. If the equations of special relativity are valid, then they must correspond to those of classical mechanics when speeds much lower than the speeds of light are considered. Let's take a look at how this affects 2 of the relativity equations we've treated. First, time, and then length. What happens if we insert ordinary, everyday values of velocity for the v symbols? When we do that, the quantity v squared over c squared is extremely small. For instance, for a jet plane traveling close to the speed of sound, v squared over c squared is about 1,000th of 1 billionth. So for everyday speeds, v squared over c squared may be taken to be 0. Let's see how inserting 0 for v affects our equations. To show for time, note our progression. That time reduces to t sub 0, our time in a rest frame of reference. We see the same for our length equation, that the relativistic length reduces to no change in length at all. Both of these equations reduce to the physics of Newton. No changes due to motion. So which is the correct physics? Einstein's or Newton's? Strictly speaking, Einstein's. But for ordinary speeds, even the speeds of spacecraft, Newton's physics is perfectly correct also. Correct enough to get astronauts to the moon and rovers to Mars. So for everyday speeds, the time and lengths of moving objects are essentially the same in both theories. The equations for special relativity, including momentum and kinetic energy, not treated here, hold for all speeds. They differ appreciably from classical equations only for speeds near the speed of light. Then they can be very different. Einstein's theory of relativity has raised many philosophical questions. What exactly is time? Can we say that it is nature's way of seeing to it that everything doesn't happen all at once? And why does time seem to move only in one direction? Has it always moved forward? Are there other parts of the universe in which time moves backward? It is likely that our three-dimensional perception of a four-dimensional world is only a beginning. Could there be a fifth dimension? Multiple dimensions? And if so, what would the nature of these dimensions be? Perhaps these unanswered questions will be answered by the physicists of tomorrow. Perhaps by that studious student sitting on the other side of your classroom? Or maybe some of your friends? Or who knows, maybe even you. In any event, physics is an exciting activity as well as an exciting body of knowledge. Yum to that. I want to leave you with a question. What exactly is it that corresponds in the correspondence principle? Until next time, good energy. Special relativity is special in the sense that it deals with only uniformly moving reference frames, ones that aren't accelerated. Not long after Albert Einstein published his special theory in 1905, he wished to include all cases of motion in his relativity theory. And between 1907 and 1915, he developed his general theory of relativity. This theory is general in that it deals also with accelerated reference frames. By imagining himself in accelerated reference frames, he came up with the notion that events in an accelerated frame of reference would be no different than events attributed to a gravitational field. The equivalence of accelerated reference frames and gravitation is enunciated in his principle of equivalence, the subject of the next screencast. Einstein applied the principle of equivalence to all physics, predicting that light bends in a gravitational field just as a tossed ball does. In fact, if both a light beam and a ball could have the same speed, bending would be the same for each. He predicted that starlight would bend as it grazes the sun. Light from B bends as it grazes the sun, making it appear to be at position A. His prediction of the exact amount of deflection of light traveling near the sun was confirmed during a 1919 solar eclipse in Africa, which propelled Einstein to international stardom. Another observation explained by Einstein's general theory was a long-known discrepancy in the orbit of the planet Mercury. Einstein also predicted that gravitation affects time. How fast the hands of a clock rotate depend on the clock's location in a gravitational field. If, for example, you move a clock from the top of a skyscraper to the ground floor, or from the surface of Earth to the bottom of a deep well, time will run slower at the point you reach than at the point you left behind. The Global Positioning System, GPS, must take account of the effect of both gravity and speed on orbiting atomic clocks. Due to gravity, clocks run faster in orbit. Due to speed, clocks run slower. Because the effects of speeding and slowing vary during each elliptical orbit, the effects don't cancel in a GPS satellite. The math is done, and your GPS tells you exactly where you are, thanks to Einstein. Einstein went further. We know that all atoms emit light at specific frequencies, characteristic of the energy differences between electron states of motion within the atom. Every atom is therefore a clock. A slowing down of atomic vibration indicates the slowing down of such atomic clocks. He predicted that an atom on the sun should emit light of a lower frequency, slower vibration, than light emitted by the same element on Earth. Since red light is at the low frequency end of the visible spectrum, a lowering of frequency shifts the color toward red. This effect is called the gravitational redshift. The gravitational redshift has been confirmed by laboratory experiments. General relativity calls for a new geometry. Rather than space simply being a region of nothingness, space is seen to be a flexible medium that can bend and twist. How it bends and twists describes a gravitational field. General relativity is a geometry of curved, four-dimensional space-time. The mathematics of this geometry is too formidable to discuss here, which Einstein begins on his classroom chalkboard. Because we are three-dimensional beings, we cannot visualize the four-dimensional bumps and depressions in space-time. Einstein himself often told his friends, "Don't try, I can't do it either." Nevertheless, we can get a glimpse of this warping by considering a simplified analogy in two dimensions. A heavy ball resting on the middle of a waterbed. Imagine the ball is Earth. The more its mass, the greater it dents or warps the two-dimensional surface. A marble rolled across the bed, but far from the ball, will roll in a relatively straight-line path, whereas one rolled near the ball will curve as it rolls across the indented surface. Imagine the moon doing that, with a curve closes upon itself, tracing out an elliptical path. Likewise, the planets that orbit the sun similarly travel along four-dimensional paths called geodesics in the warping space-time about the sun. If we substitute a black hole for the ball, the warping is severe. Anything that falls into a black hole is crushed out of existence. Gravitation is so strong that even light can't escape. Newton's theory works fine for ordinary masses, but not for enormous masses associated with black holes. There, general relativity is needed. So the presence of mass produces a curvature or warping of space-time. In Einstein's view, it is the bumps, depressions, and warpings of geometric space-time that are the phenomena of gravity. Among the predictions of general relativity are gravitational waves. Just as accelerating charge produces electromagnetic waves, accelerating mass produces gravitational waves. Evidence for them has been long sought after, with recent success. In March 2014, indirect evidence of gravitational waves of the early universe were observed from telescopes at the South Pole. An exciting find. Additional evidence is a present-day quest. As weak as gravitational waves are, general relativity assures us that they're everywhere. Shake an apple back and forth. You have just produced a gravitational wave. It's not very strong, but it exists. Time and time again, experimental confirmation of Einstein's ideas has wonderfully placed physics in the mainstream of general public interest. At the turn of this 21st century, who did Time magazine deem to be the most important person of the 20th century? That's right, none other than Albert Einstein. Seen from today's understanding of the universe, we find our importance in being very much a part of nature, not apart from it. We are the part of nature that is becoming more and more conscious of itself. With that thought in mind, I want to leave you with a question. First, we've learned that light bends in a gravitational field, that a hypothetical baseball traveling alongside photons in a light beam bend equal amounts. So my question is, why don't we notice the bending of light in our everyday environment? Until next time, good energy. We have seen that the special theory of relativity deals with frames of reference and observers that move at constant velocity. Observation from accelerated frames of reference is something else, which Einstein wished to incorporate into his theory of relativity. Einstein is often quoted as saying that imagination is more important than knowledge. There has been no doubt about Einstein's fertile imagination. Long before the space age, Einstein had no trouble imagining himself in locations far away from gravitational influences and moving at speeds near the speed of light. Spaceships were unknown in his time, although elevators were common in some cities. So Einstein imagined himself in accelerating elevators. In this lesson, we'll explain the same physics with easier-to-imagine rocket ships. In such a rocket ship at rest or in uniform motion relative to the distant stars, he and everything inside the ship would float freely. There would be no up and no down. Everything would be weightless, away from gravitational influences. But when the rocket motors are switched on and the ship accelerates, things become different. Phenomena similar to those caused by gravity would be observed. The wall above the rocket motors would push up against Einstein and become the floor. Inside the ship, he could stand on the floor and even jump up and down. For a rocket ship acceleration equal to g, an occupant waking up from a nap might think that the rocket ship had landed and was at rest on the surface of the Earth. Instead, we see that acceleration takes the place of gravity. To examine this new gravity in a spaceship, consider the results of dropping two balls inside, even of different masses. If the ship were moving with constant velocity, the balls, when released, would continue to move upward, matching the velocity of the ship. That's if the ship were moving at constant velocity, zero acceleration. But because the ship is accelerating, the floor moves up faster than the released balls, with the result that the floor soon catches up with the balls. Both balls, regardless of their mass, meet the floor at the same time. Recall Galileo's reputed demonstration at the Leaning Tower of Pisa, where pairs of balls fall together when released. Interesting how physics nicely ties together. Einstein realized that the two interpretations of the falling balls are equally valid, and he incorporated this equivalence, or impossibility of distinguishing between gravitation and acceleration, in the foundation of his general theory of relativity. Principle of equivalence? Observations made in an accelerated frame of reference are indistinguishable from observations made in a Newtonian gravitational field. This equivalence would be interesting but not revolutionary if it could be applied only to mechanical phenomena. But Einstein went further and stated that this principle holds for all natural phenomena, optical and all electromagnetic phenomena as well. Let's compare a tossed ball with a beam of light. A ball tossed sideways in a stationary spaceship in a gravity-free region will follow a straight-line path relative to both an observer inside the ship and to a stationary observer outside the spaceship. But if the ship is accelerating, the floor overtakes the ball just as in our earlier example. An observer outside the ship still sees a straight-line path. What path will an observer in the accelerating ship see? Aha! The path is curved. It is a parabola, as if the bending were due to gravity. The same holds true for a beam of light. Imagine a light ray entering the spaceship horizontally through a side window, passing through a sheet of glass in the middle of the cabin, leaving a visible trace, and then reaching the opposite wall. This would occur in a very short time, but think slow motion. An outside observer sees the light ray traveling horizontally in a straight line, and like the ball of our previous example, strike the wall slightly below a point opposite the window. But the spaceship is accelerating upward. During the time it takes for the light to reach the glass sheet, the spaceship moves up some distance, and during the equal time for the light to continue to the far wall, the spaceship moves up a greater distance. So to observers in the spaceship, the light has followed a downward curving path, bending as if it were responding to gravity. The curvature of the light is not as pronounced as the curve of the slower moving ball, but if the ball were somehow thrown horizontally across the spaceship cabin at a velocity equal to that of light, its curvature would match the light ray's curvature. Einstein carried this further. According to the principle of equivalence, if light is deflected by acceleration, it must be deflected by gravity. But gravity involves masses, and photons are pure energy with no mass. Einstein's answer was that although light is massless, it is not energyless. Gravity pulls on the energy of light because, as we learned with E equals mc squared, energy is equivalent to mass. Again, how nice when concepts tie together. Toss a ball and it curves. According to Einstein, if you toss the ball as fast as light, both would curve the same. Both paths curve equally in a uniform gravitational field. Light bends in Earth's gravitational field, but we don't detect it because the effect is so tiny. For example, in a constant gravitational field of 1g, a beam of horizontally directed light will fall a vertical distance of 4.9 meters in 1 second, just as a baseball would, but it will travel a horizontal distance of 300,000 kilometers in that time. Its curve would hardly be noticeable when you're this far from the beginning point. Aha, but this distance can be cut down between parallel mirrors. Light will reflect back and forth and fall a vertical distance of 4.9 meters in 1 second, the same vertical distance that a ball will fall in the same time. For many years, I've thought that doing this experiment would be a dandy thesis for a PhD in physics. Looking for such a thesis project, anyone? In a later time, while developing the general theory of relativity, Einstein gave a deeper explanation for the bending of light. That light bends when it travels in a space-time geometry that is bent. He stated that the presence of mass results in the bending or warping of space-time, which we don't notice here on Earth due to the relatively small mass of Earth. Close to bodies of mass much greater than Earth's, however, the bending of light is great enough to detect. Einstein predicted that starlight passing close to the sun would be deflected by an angle of 1.75 seconds of arc, large enough to be measured. My niece, Stephanie Hewitt, explains this to her class at the whiteboard. Although stars are not visible when the sun is in the sky, the deflection of starlight can be observed during an eclipse of the sun. In 1919, such an eclipse occurred of the island of Principe, off the coast of Africa near the equator. It was there that a British expedition led by the famed astronomer Arthur Eddington confirmed Einstein's prediction. Confirmation of Einstein's prediction was worldwide front-page news, which elevated him to international rock star status. Measuring this deflection has become a standard practice by eclipse buffs at nearly every total eclipse since the first measurements were made during the total eclipse of 1919. Both special and general relativity are truly fascinating fields of study. I hope these screencasts scratch your surface for follow-up study. I want to leave you with a question. The name of this screencast is The Principle of Equivalence. So my question is, exactly what is equivalent in the principle of equivalence? Until next time, good energy.